Mathematically, the factorial counts the number of ways that you can order a collection of distinct objects. While this is very useful and comes up all over the place, we might also ask, what happens if you have objects that have repeated items in them? What if all of your objects aren't distinct, and you still want to know how many ways can you order this set of objects? In order to do so, we need to modify what we're thinking about with the factorial in order to account for the fact that sometimes we're going to have duplicate or repeated items. So with the factorial giving the total number of orderings for a set of distinct objects, our question is, what happens if we have repeated items? So to motivate this example, let's consider that we have a situation where there are a total of 5 different books that you wish to place on the shelf. However, instead of them all being unique books, we have 2 copies of the first book and 3 copies of the second book. And we want to know how many ways can you order these books on the shelf. Now, what we're thinking about here is that if you have 2 copies of the same book, right, if you switch where they are in your ordering on the shelf, you haven't actually changed the ordering, right? You'd still have book A in the same places. And so we want to take that into account here. So if we didn't have any repeats, if we had 5 unique different books, there would be 5 factorial ways of ordering those books on the shelf. 5 factorial is 120, so there would be 120 different ways that you can place 5 books in an order on a shelf. Now, because of our repeats, there's actually going to be fewer orderings of these, and we can actually enumerate all of these out here. Right, so we start with A's being at the front, and then we just sort of move through, right, and pull A, B, A, and then 2 B's, and then 3 B's, and then we move our A's to the second position, right? And we just go through, and you can systematically go through and count out that there are exactly 10 ways that you can order these books on the shelves. So if there are no repeats, there's going to be 120 orderings for these. However, when we have 2 copies of book A and 3 copies of book B, there are going to be only 10 orderings. And so why did this happen? Where is the difference coming between the 120 and the 10? Well, if we had done a standard factorial, we can figure out that actually for each one of these different combinations that we have listed here, we would have counted it 2 factorial times, which is to say 2 times here, right? So if we take a look at just this first ordering, we have AA, BBB. And if we think about what's happening in our regular 5 factorial over here, well, here we're going to have one of these A's be, say, A1, and the other A is going to be A2. And so I'll denote those with just putting different colored dots on top of them, right? And so in the regular factorial, we're going to say that if you have the red dot, then the blue dot, that's going to be 1 ordering. And if you have the blue dot, and then you have the red dot, that's going to be a second ordering. Right? And so this particular combination of books would get counted twice. And if we go here, we can do the same thing, right? One time we have the red as the first one time we have the red as the second one, and then of course we would have the blue as the second, and then the blue as the first. Right? And so each one of these different combinations is going to get counted 2 times, which is to say 2 factorial times for every version of A. Now, what happens about the B's? Well, the B's is going to be the same thing, except instead of it getting counted 2 times, it's actually going to get counted 3 factorial, which is to say 6 times, right? Because you can have the green B be first. You could have that followed by, say, the blue B, followed by the red B, right? Or you could have the green B followed by the red B, followed by the blue B, right? And so forth. And then perhaps you have the green B second, and so forth, right? These 3 different items could be ordered in 3 factorial total ways. And so instead of this combination getting counted just once, it's going to get counted 6 times for every way that we can permute the B's around. And so taken together, there's going to be 2 times the number of combinations based on the A's, and 6 times the number of combinations based on the B's. And so then if we write this all down, well, what we can say is that we're going to pick one of these different orderings, right, as our first choice here. We pick one of them out, and then we pick one of the orderings of the A's, right, and then we pick one of the 3 factorial orderings of the B's, and that's going to give us our 5 factorial, or 120, right? If you take 10 times by 2 times by 6, that gives us 120. And so in other words, what we can do here is we can think about this 5 factorial that we're dealing with could be broken down for us to pick one of the unique orderings, and then to pick an ordering for the A's, and then to pick an ordering for the B's. And so if we wanted to just figure out, well, how many ways are there of picking out these original orderings, what we can say is that the total number is going to be n, which is 5 factorial divided by 2 factorial times 3 factorial, right? We could rearrange this to solve for the 10 that we actually want here. We want 10, so that's going to be our 5 factorial divided by these two here. Okay, and so if we walk through that pattern again, right, you pick a unique ordering, then you pick how you're going to order your A's, then you're going to pick how you're going to order your B's, and that has to give you the same thing as if you had just ordered all 5 to begin. So if we take this from the example to the general rule over here, right, what is the general rule going to be? Well, if we have n total objects, but there are n1 copies of object 1 and n2 copies of object 2 and so forth, then the total number of distinct orderings is always going to be given by n factorial, so the total number factorial, divided by the number of objects of type 1 factorial, the number of objects of type 2 factorial, and so forth, up to the number of objects of type k factorial. Okay. In here, we're going to have that n is equal to the sum of all of the different types, right? And so in the previous example, we had 5 total objects, 2 of the first type, 3 of the second type. 2 plus 3 gives us our 5. And this is only going to apply to situations where the copies cannot be differentiated. If all of the copies are unique, then n1, n2, n3, and so forth are all just 1, and dividing by 1 factorial a bunch of times does not make any difference. Okay, and so we can take a look at our example here. We have a box that contains 10 red cubes, 8 red spheres, 9 yellow cubes, and 6 yellow pyramids. And we want to know how many different orderings exist if the items are to be pulled from the box one by one. So we're going to just pull out all of the items here, and we're going to write down what order they come in. Okay, and so the first thing to note is that there are a total of 33 items. If you take 10 plus 8 plus 9 plus 6, that gives you 33. And so in theory, if all of the objects were differentiable, we should have 33 factorial total orderings of these. However, we know that we have repeats, right? We are going to have 10 repeats of the first type, 8 repeats of the second type, 9 repeats of the third type, and 6 repeats of the fourth type. And so then what we do is we take the total number, 33 factorial, divided by repeats of the first type factorial, repeats of the second, repeats of the third, and repeats of the fourth. And so then if you work this out, we get this incredibly large number over here, right? But this is ultimately going to follow this pattern that we were talking about here. Now, let's suppose, to extend this out, that we ignore the color, right? So the color doesn't actually make any difference. How many different orderings are going to exist if items are to be pulled from the box one by one? So what that is really telling us is that if we look at our red cubes and we look at our yellow cubes, those are now the same shape, right? And so here, what we could say is that we were going to have 10 plus 9, so that's 19 of the first type of item, right? We're going to have 8 spheres and 6 yellow pyramids. And so we're still going to take our 33 as our total, right? Because we still have the same total, but then instead of it being 33 over 10 factorial times 8 factorial times 9 factorial times 6 factorial, it's going to be 33 factorial divided by 19 factorial, where we take our 10 plus our 9, times 8 factorial times by 6 factorial, right? And so we can work through all of this. 33 total items, n1 is 19, n2 is 8, and 3 is 6, and thus our total number is given to us by that expression. Once again, we're dealing with a very large number there. So if you want to count the orderings when you have non-distinct objects, what we have to do is we take the factorial, which counts our orderings of distinct objects, and then we modify it. We divide by the different ways that we could rearrange the same objects. And so make sure that you're walking through that process of thinking about them all as distinct first, and then not double counting all of the repeated patterns, right? But in this case, now if you wanted to have a set of objects, they can be arbitrary. Some of them might be repeated, some of them might not be repeated. This rule is always going to apply, and it's going to tell you how many ways you can put a set of objects, distinct or otherwise, in order.